Hey everyone, and welcome. I am absolutely thrilled you're here with us for this explainer. Today, we're taking a really fascinating journey straight into the heart of control theory, and we're going to break down the mathematical modeling of systems. If you've ever found yourself wondering exactly how engineers get complex machines, circuits, or even completely wild biological processes to do exactly what they want them to do, well, you are in the perfect place. We're going to unpack these concepts step by step, taking some pretty messy physical realities and translating them into super elegant, workable math. So let's just dive right in. So think about this for a second. How in the world do we actually force a totally chaotic system to obey our commands? I mean, picture a drone trying to stabilize itself in the middle of a windstorm, or even just your car's cruise control keeping you at exactly 60 miles per hour as you're going up and down steep hills. The physical world is messy, it's unpredictable, and it is absolutely full of random disturbances. And yet, mathematical control theory gives us the exact tools we need to completely tame that chaos. It really isn't magic, it's just math. But before we can actually control that chaos, we have to know how to model it. All right, here's our game plan for today. We're going to hit 5 main stops. First, controlling dynamic systems. Second, creating the mathematical model. Third, the CISO approach in time. Fourth, 3 key properties. And finally, describing continuous time. Okay, jumping right into section 1, controlling dynamic systems, or basically, understanding natural behavior. Because obviously, before we can even hope to command a system, we really have to understand its natural, unforced state. Our source material actually uses this fantastic French word for this concept, asservissement. It roughly translates to control, or even literally enslavement. Sounds intense, right? But really, it's just the action of modifying a system's behavior to impose a specific desired outcome. And honestly, this is the ultimate goal of the entire field. We basically want to feed a command, an input, into a system, and just totally force the output to follow that command reliably, no matter what kind of crazy external perturbations or disturbances are trying to knock it off course. Now, you've kind of got 2 distinct phases here as an engineer. Analysis versus synthesis, and you absolutely cannot skip that first step. Analysis is all about just observing the system in its natural state, asking what are its inherent properties, what are its actual physical limitations. We have to know exactly what we're dealing with. Then, and only then, can we move on to synthesis. Synthesis is the fun part, where we actively develop a control law, like a mathematical controller, to impose new performance standards and essentially bend the system entirely to our will. Moving right along to section 2. Creating the mathematical model. This is where we translate reality into equations. Because to do any of that analysis we just talked about, we literally have to abstract our physical reality into something we can calculate. When we're building these models, we basically have 2 buckets to choose from. First up, we've got knowledge models. These are also known as phenomenological models, and they're built from the ground up using the strict laws of physics, chemistry, or biology. Every single variable in these equations actually means something tangible in the real world, stuff like mass, friction, or electrical resistance. Then on the flip side, we have behavioral models. These are essentially just black boxes. You build them entirely by measuring data, basically seeing what output you get for a given input without even worrying about the underlying physics. Behavioral models are kind of the shortcut for when we don't really want to do the heavy physics math. But for the scope of our explainer today, we are going to focus exclusively on knowledge models. Which brings us to section 3, the CISO approach and time. This is all about reducing complexity, filtering our scope down even more to make things actually manageable. The real world is full of MIMO systems, multiple input, multiple output. Think about flying a helicopter. You've got all these multiple controls affecting multiple axes of flight, all at the exact same time. It gets incredibly complex really fast. So to build a rock-solid foundation, we're stripping all of that away. We're focusing strictly on CISO, single input, single output. In our operational notation here, U of t is our one single input. It goes straight into our system, represented by that big S, and spits out our single output Y of t. It is just a beautifully simple, clean cause and effect relationship. But hey, notice that little t in the parentheses? That stands for time. And we've actually got to decide how we want to measure time. We have 2 main choices, continuous time or discrete time. Continuous time is kind of like a smoothly flowing river. The variable t belongs to the set of real numbers, which just means changes happen fluidly and constantly, and we usually describe that using differential equations. Discrete time, on the other hand, means t belongs to integers. It's digital. So discrete time isn't a smooth flow. It's chunky. It's a sequence of distinct steps or events. You measure the system at time 1, then time 2, then time 3. You don't know, and frankly you don't care, what happens in the exact fractions of a second in between those points. Now, while discrete time is absolutely vital for modern computer control, for our mathematical modeling focus today, we're going to stick with the smoothly flowing world of continuous time.
All right, section 4, 3 key properties, basically the rules of the game. For our mathematical models to actually be solvable and useful, the continuous SysO systems we're looking at have to obey 3 foundational laws.
To wrap our heads around the first rule, there's this great analogy from the source material. Just imagine the circular waves propagating on a lake when you throw a stone in. You get a really nice, predictable set of ripples, right? Well, what happens if you throw 2 stones into the lake at the exact same time? You get 2 sets of waves, and when those waves meet, they simply add together. They overlap without destroying the fundamental shape of the other. This mental picture of the overlapping ripples perfectly illustrates the principle of superposition. And that lake picture flawlessly defines our first major mathematical property, linearity. In a linear system, the effects produced by different causes just add together nicely. Plus, if you multiply the input by a certain factor, say you chuck a rock that's twice as heavy, the output is multiplied by that exact same factor. The waves are literally twice as big. Honestly, linearity is a massive blessing for engineers. Non-linear systems are incredibly chaotic and tough to predict, but linear systems behave predictably, proportionally, and logically.
Rule number 2 is causality. This one's super intuitive, honestly, because it's just a logical necessity in the physical world. Causality simply means that the output of a system at any given moment depends totally and exclusively on what happened in the past. The effect can never ever precede the cause. A system literally cannot react to an input before that input has actually been applied. Makes sense, right?
And our third and final rule is stationarity, which you might also know as time invariance. Literally, if you delay your input by 5 seconds, the exact same output will occur, just delayed by 5 seconds. It means the underlying physical laws governing our system don't spontaneously change as the clock ticks forward. A motor is going to behave the exact same way on Tuesday as it did on Monday. So just to recap, we are looking for systems that are linear, causal, and stationary. Okay, final stretch. Section 5, describing continuous time. We've defined all our parameters, and now we arrive at the very bottom of our conceptual funnel, the final equation. Since we're living in this continuous time, linear, stationary world we just built, the absolute best way to describe it is using a differential equation with constant coefficients. We've got the sum of the derivatives of the output on one side and the sum of the derivatives of the input on the other. And I really want to highlight the parameters n and m here. They represent the highest order of derivative for the output and input. For this mathematical model to actually obey our rule of causality, meaning, the system isn't magically predicting the future, the highest derivative of the output, n, absolutely must be greater than or equal to the highest derivative of the input, m. If it isn't, the math literally says the system is reacting to things before they even happen, which obviously is physically impossible. But let's take a step back and really look at that equation for a second. Look at all those derivatives. Naturally, you're probably thinking, are these differential equations just too incredibly complex to solve practically? And honestly, yeah, they kind of are. Even though the time domain is the most natural way to view a signal, trying to solve complex, high-order differential and integral equations by hand every single time you want to analyze a system is just tedious. It's a huge bottleneck, and it's super prone to errors. But, thankfully, there's a mathematical magic trick that totally saves the day. Enter the Laplace transform. It takes these nightmare differential operations, the ones that give engineering students cold sweats, and completely shifts them into a different frequency domain. And when it does that, the complex calculus just vanishes. Those derivatives magically transform into basic, simple algebra, just addition, subtraction, multiplication, and division. It is literally the ultimate tool for system analysis. But exactly how does this mathematical sleight of hand actually work? Well, that is a fantastic question, and it's exactly what we're going to explore next time. Thank you so much for hanging out with me for this explainer. Keep wondering, keep learning, and I will see you next time.